We discussed the issue of having conventional reinforced concrete beam versus pre-stressed beam and the type of loading, type of stress is going to happen within the beam. So what we said is in conventional concrete beam, you have the loading coming to it. And once you start to apply the load, and of course the load is not getting applied all of a sudden, but it's going to be gradual application. So let's say, for example, at the beginning you start, let's say, with 1 pound per foot, and then you make it 100, and you make it 1,000, till you reach, let's say, the capacity of the beam, right? At the beginning, if you have no loads at all, no stresses, the beam is not stressed. You start to apply loads gradually. It's going to be incremental load, and then at a certain point, the beam is going to start to crack. And once the beam is going to start to crack, you're here activating or triggering the force in the reinforcing bars. So before you trigger the force in the reinforcing bars, the beam is not cracked yet. After that, now the beam rebars are going to start to take some tension force. It's going to continue with you. The crack is going to extend. Neutral axis is going to start to come from the middle. The mid height of the beam is going to be shifting up. Usually, the zone is going to be severely cracked. It's going to be right in the middle. This one you have the maximum moment. Once you go right and left, the amount of moment is going to drop down, and the amount of cracks also is going to be reduced. Meaning, no load, no stress in the beam. This is not the case in pre-stress beams, whether it is pre-tension or post-tension. Once you apply the tension force on it, which means once you put here the compression force on the concrete, because when you apply tension on the reinforcing bar, on the pre-stress tendons or the cables or the strands, it means that you are putting actually in the concrete, you are putting force. Meaning, when I apply here tension force in the strands itself, you're going to be putting compression force on the beam. So before you start to apply any loads, just under the self weight, you'd like here to look at the beam, right? When you just have the self weight, you'd like to see here some camber. Camber means something opposite deflection, which means the beam is going to be going up. The amount of camber is going to be this distance from here, from the bottom of the beam when it cambers up, all the way to a straight line in the original position. We call this amount, let's say 2-3 inches, we call this going to be the camber, which is opposite of deflection. Now, you start to apply here the compression force on the beam, which means tension force on the strands, and then the beam is going to start to camber up, as if you're pushing it up, because you're applying an opposite moment. This is just for the self-weight. Now, dead load is composed of what? Of self-weight and additional dead load. So I'm going to say here dead load. It's going to be composed of self-weight plus additional dead load. In the business of pre-stressed concrete, we call it superimposed dead load. So dead load is composed of, I'm going to say total dead load equals dead load, which now is a self-weight, plus superimposed dead load. So superimposed dead load is the same as this additional dead load. In conventional concrete, we just quote additional dead load. In the pre-stressed concrete business, we quote superimposed dead load. Both of them, they are part of the dead load, like the total dead load. So you'd like this beam here, once you add the dead load, that you'd like to see here a flat beam, which means no camber, no deflection. And this can be tough to attain, because the question is, what's the certainty about putting this compression force on the beam is going to stay there? It's going to be one question, right? The other question is, when you say here dead load, what's the certainty that you're going to have exactly the dead load that you designed for in terms of the self-weight and the additional dead load? Because this number is just design values, and most likely the value is going to be increased. Just to be safe, when you put this pre-stressing, you put enough pre-stressing so that you'll make this flat. And because of this uncertainty, we're going to say maybe you'd like to stress it to balance, which means to bring this force down, right? You'd like here to balance, I'm going to say here maybe 75% dead load, right? Now, which dead load? Total dead load? You say yes, total dead load. Let's say to 90%. So it's going to be 75 to 95 to 90% of, let's say, total dead load. You don't want to go beyond this. You don't want to do lots of pre-stressing, and then all of a sudden, the beam is cambered up, and then you put the additional dead load or superimposed dead load, and then you put life load, and you still have this camber. This is not going to be good performance. I mean, you don't want to see this. And the code is not really addressing this issue. This is going to be usually based on practice. They say, do not try to keep it like this. But instead, the code would give you stress limits. If you keep the beam within the stress limits, you're going to find out that the appropriate value to use in the pre-stressing is going to be 75% to maybe to 90% of total dead load. So it's true that the code doesn't say anything about this total dead load and the balancing load, but they give you stress limits. We call it here stress state. Now, pre-stressed, again, when you put the full service load, what's the full service load here? I'm going to say full service load, meaning I'm going to put here dead load plus superimposed dead load plus life load. This is going to be the total service loads or the full service loads. Once you put them all together, you're going to see a little bit of deflection, which is acceptable as long as you're going to be within the code limits. And of course, you're going to see some cracks. The good thing about this pre-stress, you can control the amount of cracks that happen here in the beam. You can design for uncracked beam if you want to. So you can say, I'd like my beam to be free of cracks, or I'm allowable here a certain amount of cracks. You don't have this luxury when it comes to conventional concrete. In here, you cannot really control this. But in pre-stress, you can control the amount of cracks. We looked here at just underloading, and then we're talking here about loading plus pre-stress. So for this type of loading, as you see here, and let's just assume for a second here that the beam is homogeneous and there is no cracks yet. You apply some loading, this is going to be the type of stress that you're going to be developing. C stands for compression, T stands for tension. So this is not top and bottom. Sometimes we say top and bottom, sometimes we say just compression and tension. There's sub L, this sub L is because this is due to the loading. So this is the reason I called it this way. Now, when you take here the amount of force P, which means this one here, it's going to be from pre-stressing, right? Now you add it to the loading. So what you need to do is just to take the stress distribution that you put right in here and just copy it in this place. You just put it right there. And then you add the stresses from this loading to the stresses from the axial load P. If you put this axial load right in the center, in the CG of the section, you're going to have here uniform stress. It's not going to be a change like tension compression. But in here, you're going to have tension compression. Take this distribution plus this distribution, you end up with more compression because guess what? This compression on the top is going to increase and the tension at the bottom is going to reduce. And this is due to what? Due to having the regular loading, the standard loading that we have, the service loading, plus an axial load that when you put it right at the center of the beam. Not the best idea, but it happens. In many cases, I've seen it. Like in precast members, you just do it this way because it's just cheaper. It's easier. And they're not looking for this high performance. They just need to have a tight wall free of cracks and no leak. Let's say that you're going to put the structure in some water or whatever, right? And some fluids, and you'd like to minimize the amount of leak. Now look what happened here at the stress. You see this stress here, F top, is going to be equal to what? FCL coming from this side plus FCP. I understand this is going to be negative and negative, right? But I'm going to call it just positive value, and I mean for the symbol itself. And then the value of this FCL is going to be negative. at the bottom is going to be equal to FCP plus FTL. This here is going to be negative and this is going to be positive, right? They're going to be kind of trying to balance each other. At the end, you may end up with some tension. Now, the loading here, this FCL and FTL, compression and tension due to loading, is going to be just equal to the moment applied here divided by the section modulus. This section modulus, if you like, the equation for it, you know that everybody knows this, is going to be S equals, you can say I divided by C, and C in this case is going to be 1/2 of the height, which means from here to there. It's going to be C. When you have rectangular section, this is going to be C on the top, is going to be C at the bottom, because you can have here C top and C bottom if you like, call it this way. And from the axial load, it is simply, you can just say that the pressure or the stress here is going to be equal to P divided by the cross-section area of that section. Now, the best way, if you like, is just put the strand at the bottom, all the way at the bottom of the beam. And when you do this, you counteract the effect of this loading because you are pushing this up, like what happened here in this picture. When I start to put here the pre-stress at the bottom, I'm pushing the beam up, which means I'm balancing the effect of the loading. So I'm counteracting the effect of this loading. So this actually is going to be a better idea than this system here. This system, when you put the strand in the middle, it's not a very good idea. Maybe you'd like to put at the bottom to push this up and to balance the loading coming to it. So when you do this, look at the stress here. It's kind of more balanced. If you just look at the loading here, the amount of big tension that you put here in the bottom coming from the loading is going to get reduced. Why? Because you have your compression coming from the pre-stressing. And the amount of compression here that you have on the top, what's going to happen to it? It's going to get reduced. Why? Because from the pre-stressing, you're going to have some tensile stresses. So actually, you're helping the beam. You're trying to reduce the stresses here on the top, but you put higher quality strains. So once you have this eccentricity, the pre-stressing here is going to have two components of the stress. So in the past, it used to be just P over A. But in this case here, it's not just P over A. It is P over A plus P times E, which means the moment coming from the pre-stressing divided by the section modulus. So we have here two sources, right? When it comes to the pre-stressing. So coming from the pre-stressing is going to be P over A. And then the top, you're going to have some tension force, right? So this is going to be CP, the compression, and it's going to be tension on the top. So on the top is going to be the moment divided by S. This is going to be the moment. We call this eccentricity. So I can spell it out here. E, eccentricity. Can someone help me here and say what is the opposite of eccentricity? What's the opposite of eccentric? So for example, you can call this eccentric loading. What's the opposite of this? Help. Concentric. Thank you. This is correct. So I'm going to say here concentric. Concentric loading. So what does it mean by concentric loading? I'm going to say like this case. This is going to be actually concentric loading and it's going to be eccentric loading. So the stress here is going to have two terms, negative P over A, and then you have here PE over S. One time you're going to have it as positive, like for tension, and the other time is going to be compression, right? It's going to be negative. This is okay. Now I have three types of stresses or three different stresses that I need to up and together. And this is true. You have one coming from the loading, one coming from the pre-stressing force, and then one coming from the eccentricity. I understand that both of these two terms can be from the pre-tensioning or the post-tensioning, if you like. But one of them because the axial compression, and the other ones because the eccentricity on the beam from the pre-stressing. Now, when it comes here to the applied, because I have here two sources, right? I'm going to say You can call this to be 1 coming from the loading, and then you're going to have this 2 together. It's going to be the stresses coming from the pre-stressing, right? Yes, okay. Now, first the loading, this M. M is going to be the applied moment. It is not going to be P times E. P times E is going to be the eccentricity from the strains to the beam. So we can say, okay, applied loading, M total is going to be M dead load, superimposed dead load, and you have also life load. Let me go back here. I'm going to say loading. What loading are we talking about? I'm going to say dead load, superimposed dead load, and life load. Like what we have done here, right? Total dead load, it means dead load plus superimposed dead load. Total load is what? Is going to be life load plus dead load plus superimposed dead load. And this is exactly what we are looking at. Dead load, superimposed dead load, and life load. Now, this is going to be the moment coming from the system. When we build the concrete pre-stress beam, we just do the dead load first. It's going to be the self weight. And then we apply the pre-stress. And of course, the pre-stress at the beginning is going to be kind of a little bit higher than the effective value. So at the beginning, you're going to be applying high pre-stress value. And over time, you're going to be losing some stresses. And it is written right here. We call this time-dependent losses in the pre-stress. This happens mainly because two main issues. The two big main issue, right? The time-dependent is going to be actually called creep and shrinkage of concrete. Creep, by definition, is going to be the long-term stresses under constant loading without adding any new loads. It's going to be just relaxing. And shrinkage, you know, the shrinkage doesn't happen all of a sudden in one time. It just takes time. We have some instantaneous losses, like, for example, slippage is going to be kind of mechanical losses. It happened right at the time of pre-stressing. Once you're done with the pre-stressing, you're going to have some slippage. It's going to happen in the anchorage. So we call this instantaneous losses. So when we start at the beginning, we start with the force. So the force here, later on, I'm going to call it PI and PE. PI is going to happen when you have only dead load. PE is going to be the effective. It's going to happen when you have dead load and superimposed dead load and total load. And usually this PE is going to be lower than PI because PI is going to be the initial pre-stress. You're going to start with high losses, high pre-stress forces, and then over time, you're going to have some losses. So the stress is here, top and bottom. Now I'm going to stop saying compression and tension because it depends on the amount of force that you put in there coming from the moment, the applied moment, and also depends on the amount of pre-stressing. Someone's going to say, how would you confirm, if I may go back here, how can I confirm here that the top you're going to end up with compression, here's tension? Because in some cases, if I have here big loading and the amount of pre-stress is going to be very low, look at this. When you have big load, which means big positive stress, right? And the amount of pre-stress is going to be very small, you end up with tension. But what happened here, if I have very limited live load and dead load, right? The loading is going to be very small. And the amount of pre-stress is just high. So this compression values in value, like the numeric value is going to be high, and this is going to be very small compared to it. In a case like this, you may end up with compression stresses. So it is not true that you usually end up here with some tension, top is going to be compression. This is not true. It could be different. It just depends on the values. And you can play with this if you like. So what we're saying here, we're just going to call it F top and F bottom. And if at the end, I'm going to have here a positive value, it means that I have tension. If I have negative value for F top, it's going to be compression. Same thing at the bottom. I may have tension or compression, right? So T stands for top, B is going to stand for bottom. You can say here I have three terms. The first term is going to be from the axial compression. So when you use this equation here, if you like to use it, this P is going to be just numerical value, absolute value. It's going to be usually positive. Why? Because the effect of it as being compressive force on the concrete is going to come from this negative sign. You say, okay, now it's going to be in the top. Usually, you're going to put the strand at the bottom. So I'm expecting here that the second effect, which is eccentricity, if I just use positive value for P, can end up with some tension force or tension stresses on the top. And this P times E means the moment due to eccentricity multiplied by C, which means 1/2 of the depth if you have a rectangular section, divided by I gross. You can call it IG or you can say IC, it doesn't matter. Sometimes you call it IC for concrete. It means you are not considering here any cracking. This is the bottom line. And then because the loading is going to be causing compression on the top, therefore this moment here is going to be absolute value for the moment, right? And this moment can be just dead load, it can be live load, it can be dead on live, it can be dead and superimposed on live. It depends. It's just general equation. And same thing, C divided by IG. For the bottom, we can do the same, but instead I'm gonna have here negative sign because at the bottom, I'm gonna have the strand on the bottom, it's gonna be causing compression for the moment. And then from the loading, so this moment is a loading, I'm gonna have positive value at the bottom because the tension is gonna be at the bottom for simply supported beams. Like what we discussed last time, we said I can play a little bit with this moment of inertia and see and just rewrite the equation. And for that, I'm going to say the stresses here, right, is going to be coming from two sources at the beginning, right? And these two sources is going to be from the pre-stressing. So the first one is going to be PI divided by AC. And once you multiply it here by 1, it means that you're taking the effect of the compressive force on the concrete. And once you start here to add the eccentricity, I'm going to say this term here is going to be for the eccentricity. And same thing is going to be F top and bottom. So both of these two equations, actually, this can be just for the pre-stressing effect on the beam. So, okay. How about the effect of the applied load? I'm going to say effect of the applied load is going to be coming right here. See, and I have some shading for it, right? It's going to be the effect of the applied load. And this term here, right, top and bottom is going to be the effect of the pre-stressing. Okay. So at the beginning, I have only the self-weight of the beam. When you have the self-weight of the beam, it's going to be M dead load. At that point, I'm going to have PI. Now, what is PI in this case? I'm going to say PI is instantaneous pre-stress force, the initial one at the beginning when you apply the pre-stress. I'm expecting here high stresses or high forces coming from the pre-stressing. Later on, this value is going to drop down. At that point, I'm going to be applying dead load, live load, superimposed dead load. Okay. So the basic concept here, if you'd like to put this trends, you're going to put it at the bottom. If you have uniform load, you'd like to put it in this trapezoidal, in this parabolic, let's say. And if you have a point load, maybe you'd like to do it as a straight line. So the eccentricity that you have, you're going to have some eccentricity here in the midspan and maybe another eccentricity here at the beginning of the span, at the support. In some cases, you'd like to take this and just take it to the CG, which means take it to the neutral axis. In a case like this, once you put here the compressive stress or compressive force right here at this location, right, or maybe here, let's say for a second that I'm going to put it right at the CG. It means for the analysis of this section, I don't have eccentricity. But for the analysis of this section, I'm going to have some eccentricity. Okay, now let me take you back to the previous slides. It means for the middle section, you can apply this equation. But once you take it here to the support point, let's say I'm looking here at this equation. So when you have some eccentricity at the midspan, yeah, you can use this E. But once you go here to the beginning at the support, what's going to happen? This term here is going to vanish because you don't have E is going to be equal to 0. And also because the applied moment due to loading is going to be also equal to 0, this is going to be also vanishing. I mean, both of this term is going to be gone. And you'll end up with just P over A, which is fine. Concrete is going to be good in compression. So some idea maybe to finish the strand or to start the strand from one side and finish at the other side, you're going to put it at the CG is going to be acceptable. And in some cases, you'd like to have a little bit of eccentricity. Because someone can say here, how would you tell that usually moment diagram is going to be equal, the applied moment diagram, right? Due to applied loads, is going to be equal to 0 at each end. The middle is going to be max. In some cases, we end up with some clamping here, meaning if I have a column, if I have a connection, right, I can maybe develop some moment at this location. And if this is the case, you may not end up with a 0 moment at the support, because in reality, you don't have this pin support. It doesn't happen like this. So if you're going to be developing here some moment in the beam, why don't have some eccentricity for it? And this is also acceptable. Now let's look here at the stress distribution due to different loading. So I'm going to say, okay, here's the section. Here's our section, right? It's kind of irregular, like the bulb section for bridges. It does really need to be rectangular section. It's okay to have a section like this. And for this from the neutral axis, right? The point of application of the pre-stressing is going to be called E, the eccentricity. And this is going to be at the middle span, in the middle of the beam. This one here, the distance from here to there, this dimension is going to be called C top, and this is going to be C bottom. Okay, good. Just because of the applied axial load, which means P here, of course, is going to be at the beginning PI. We're going to have a stress, uniform stress distribution is going to be equal to PI over AC, the area of the concrete. It's going to be all compression. So this red line is the data. It's like the baseline, right? When you draw the stresses. Because the eccentricity that you're looking here at, I'm going to have also some distribution. Of course, at the bottom is going to be compression, top is going to be tension. So the first term here, this is going to be just for the axial force. Second term, second distribution, this is why it says plus, is going to be because eccentricity, right? And both of them, they're going to give me a total distribution like this. At the bottom, I'm going to have here some compression, lots of compression. In the top, I may end up with maybe some tension, or sometimes I may end up with a little bit of compression here. So it depends. Sometimes it's going to be like this, or it's going to be like this. It depends on location of the strand and the amount of jacking force that you put to it, like the pre-stressing force. So what I have here in this section, I have the effect of pre-stressing. So this is total pre-stressing, right? I'm going to have axial compression and eccentricity. It's going to give me this. I'm going to start here to apply the load. So in the second phase of loading, I can just take this loading, this load distribution, and just transfer it here. I'm going to say, okay, now I have pre-stressing. Now I need to add the dead load to it. I'm going to say, what does it mean by dead load? Dead load here, in this case, in pre-stressing, is going to be the only thing, right? It's going to be the self-weight only, and that's it. No additional dead load is going to be added to it. So what's going to happen? I'll just take the stress distribution, and we're going to be adding here the effect of the dead load. So what do? You add the stress value here to the stress value here, put it right there. Then you add the stress at the bottom. With the stress at the bottom, you put it here. Again, I'm not sure. It depends on the design. Sometimes you have the stress like this, sometimes you have it like this, right? But when it comes to dead load effect or any gravity loading, I'm expecting the top is going to be compression, the bottom to be tension. Now you add the two stresses to each other. Now this is going to be the stage of the stresses that you have, and this includes what? Axial load, eccentricity, and dead load only. So in this case, this is going to be PI, the initial pre-stressing. You still have lots of stressors locked in. Over time, you're going to be losing some of the stressors. So what happened to PI will becomes PE. So the stress here is going to drop down a little bit. Why? Because you're going to have some losses in the stresses, in the strengths. Now you have the life load and you have the superimposed life load. So look what happened to the stresses. This is stress here that I just reached to, the stress distribution. I'm going to be copying it here. But I'm going to reduce the force, right? So it's going to be the same equation. But instead of PI, I'll make it PE. And PE is going to be slightly less than PI. Like, how much drop are we talking about? I'm going to say, let's say 12% to 15%, right? Sometimes, of course, depend on the aggregate, the location, and the practice. I'm going to say maybe to 20% losses. So PI is going to be larger than PE by 20%. let's say 15% on average. So the stress is going to relax a little bit, the stress distribution, and then we're going to copy it here. And then now we're going to be adding the superimposed dead load and the live load stress distribution. And for that, we're going to have the total stress distribution is going to be right here at this location. So you cannot really take the effective stress from the beginning, PI, and just add all the stresses to each other. You need to look at the steps and what happened to the stress distribution. And then you need also to understand that at this stage of loading, it is true that you have kind of some fresh concrete at the time of applying the stresses. The concrete is not 100%. So the F prime C is not really at 28 days, and most likely maybe it's going to be at 7 days or maybe 10 days. Sometimes at 4 days, depend on the curing process or technique that they use. And for that reason, we'd like to check here the stresses, tension or compression, top and bottom, when you have the concrete is kind of fresh. And again, you'd like to check here the stresses, top and bottom, when you have the concrete 100% hardened and you are maybe above 28 days of fabrication. So, okay, good. Now, as you see here, this is going to be the same equation that you used previously. I'm going to take you back here and say, oh, this is going to be the same equation. So what happened? In this equation here, it says when you have PI, which means at the beginning of the stressing, this PI is going to be the high value, and you have only dead load. And this is going to be the equation that you need to use, F top and F bottom. Good thing, you're going to have your formula sheet on you. And you don't have here any problem trying to memorize that. So again, when you check here for dead load, you got to be at PI level. PI level means that you have here higher stresses. But if you like to check here for total load, we're going to be 100% sure that PI has been dropped to PE. So PI is going to be the higher value, and PE is going to be the lower value. And these two equations, they're going to be good to check the stresses. But in this case, you're going to have the total moment. In this case here, when you have the PI instantaneous or initial stress, you're going to be at dead load, only dead load, which means self-weight. But once you become here to the effective stresses, you're going to be at M total. All right, so this is going to be the tricky part. This is the part that we really need to understand. When you have here dead load and live load and the whole thing, right? We're going to be taking this is actually just enlarged version of the stress distribution, which means of this. I've just taken this, enlarged it, and now I'm going to be, I want to study it a little bit further. So, okay. During the service life of this bridge girder, how much stresses would you like to see here? Because this now is going to become what? Look at this. This is going to be from pre-stressing, so this is going to be the positive side, right? I'm going to have here some tension. If you really would like to have a beam free from cracks, right? If this beam here, this pre-stress beam, will have no cracks at all. Let's say because the bridge that you put there is just running above, let's say, a section of the ocean, and you have harsh environment, you have lots of chlorides, you have lots of sulfate. So what would you do here? You'd like to reduce the amount of stress in your analysis here, because when we studied the cracking point in concrete beams, we say it's going to be cracking at, if you remember, 7.5 square root of F prime C. But in here, I can control the crack if I limit the final stress at the bottom of the beam, the tensile stress. Let's say, for example, to 6 square root of F prime C. If I can be sure or confirm to you that the stresses here will not go beyond this limit, what would you say? Would you expect any cracks to happen here at the bottom of the beam? You're going to say no. I can't do this in conventional concrete beam. In cast in place concrete beam, non-pre-stressed, you cannot do this because you're going to have lots of tensile stresses and the rebar is going to get triggered and they need to help you to support the loading. But in pre-stress, I can control the amount of the stress here at the bottom by controlling the amount of pre-stress I'm going to put here. And if I can confirm to you that the tensile stresses at the bottom of the beam wouldn't go above or beyond this limit, it means I can have a beam free from cracks. I can do it. I mean, you can just play with the numbers. We have here a couple of methods to find out the stresses and to study the stresses and the loading. One of them is called centerline method. And you can use it. There is nothing wrong with it. And it does here first, maybe you'd like to compare between conventional beam and pre-stress beams. So this one here is going to be the conventional beam, reinforced concrete beam, and it's going to be pre-stressed beams. The purpose of this method is not to do any analysis with it, actually. And the purpose of it is more understanding of this tension compression, the TC couple that we have discussed before. You'd like to understand what happened, what the difference between this concrete beam and this pre-stress beam. What's going on there in terms of internal forces. And then they give it to you here with this incremental loading. So at the beginning, they say, what happened when W is going to be equal to 0, right? Same thing here, WC. So you compare here a loading level with a loading level, conventional concrete and pre-stressed concrete beam. Now you start with here the loading, and then you code just W1 because you put your incremental loading, right? And then at the end, you reach this, let's say to your design load. What's going to happen? Same thing in the conventional concrete and the pre-stressed beam. What happened at the beginning, right? You put no load. And the beam is just sitting there. No load at all. In conventional concrete beam, tension force location is going to be right here. Compression force location is going to be right there. Let's say at A/2. If you remember compression block depth that we used to do, you say, okay, this is going to be here at A/2. Maybe at the beginning it's going to be equal to 0 because there is no forces, no loads, no stresses at all in the steel or the concrete. But once you start to add here a little bit of load, what's going to happen? Tension force is going to start to develop in the tensile rebars at the bottom, and some compression force, and location most likely is going to be almost the same. It's not really changing much. This is under the applied loading. So once you start here to apply some load, you're going to have some compression and some tension. They're not going to be equal to 0, but the location of the force is the same. It's not really changing. And once you go here to the final design load, location of the force is going to be almost the same, but the force is going to be developed more and more. It's going to be just going higher. And the moment at any point is going to be either tension or compression multiplied by this A. This A, which means D minus A/2. This is going to be the standard, right? For this one, D minus A/2. In pre-stressed beams, performance is going to be completely different. Now let's look what's happening here. You have no loading, but the beam is stressed already because you have this compressive force on the beam from the pre-stressing. So in a case like this, because of equilibrium, right, this force, the compression force, it has to be aligned with the tension force. And this is true because you don't really have any external forces applied. You have no loading applied on the beam. So, okay. The moment here, if I may type here, I'm going to say the moment equals C or T, I'm going to say times A. Like the arm, the moment arm. And the moment here, the applied moment or external moment is going to be equal to the internal moment. Your external moment is going to be equal to, let's say, W squared divided by 8 is going to be equal to 0. Therefore, the internal moment has to also be equal to 0, because if the two moments are not equal to each other, this beam is not in equilibrium. Okay. So if this moment I know is going to be equal to 0 and this A is not equal to 0, therefore this C and T, they have to be equal to 0. This is how I concluded here that I'm not going to have here any forces, right? This is going to be here equal to 0 because A has numerical value. Now let's move here to this case. In this case, the moment also, external moment is going to be equal to 0. And the internal moment and external moment, they have to be equal to each other. If they have to be equal to each other, it means, again, moment is going to be equals to C or T multiplied by the moment R. But the compression force that you have in the concrete, it has a value. Therefore, the moment arm itself, it has to be equal to 0. This is why the compression is going to be aligned with the tension, the way that you see it here. Now I'm going to start to apply some load. What's going to happen? Moment is going to have a value. And the moment, again, is going to be equal to T or C multiplied by the moment R. The T or the C is constant because it's going to be equal to the pre-stressing forces that you put in there. So what's going to happen? The moment arm is going to start to develop because the applied moment external is going to be equal to the internal, and the internal here equals to, let's say, T multiplied by this A. The tension or compression force is just constant. So when this becomes constant here and you have this new moment value, it means that A is going to start to grow up in value. When you have here the maximum moment, right? Once you start here to apply lots of moment, now you are becoming here, you are at the surface level. Once you become here at the surface level, what's going to happen? This compression force is going to be jumping up more. When this goes up, it means the moment arm is going to increase. So in this case here, moment arm is going to be equal to 0 because the two forces are going to be aligned with each other. In this case here, with this loading, let's say that this compression force is going to be right at the centroid at the given point. And in this case, the eccentricity of the cable is going to be equal to the eccentricity of the compressive force. And this is exactly happening when you have the beam flat. If I may take you back to this slide, it is happening at this situation. If this makes sense. At the beginning, you have the beam cambered, and then once you put the dead load, you'd like to make it flat. So this location of the force right here is going to happen when the amount of dead load is going to be causing deflection, and this deflection exactly equals to the camber by the pre-stressing. In a case like this, the compressive force is going to be right at the centroid of the section. So okay, but here, look what happened here. This moment arm, which is A, is going to be composed of two segments or two sections. One of them is going to be the E, the eccentricity of the cable, plus E prime. Therefore, E prime is going to be equal to A subtracting E. So okay. Let's see what is the use of this. So let's take here this. We're going to be taking this end of the beam, compressive force at the surface load, tension force is going to be, of course, at the strands. Total eccentricity or total moment arm is going to be equal to A, composed of two terms, E plus E prime. And the moment here is going to be equal to C times A or T times A, one of them, and they're equal to each other. It doesn't matter. You just take one of them, multiply by A. Again here, E prime, which means the distance from the centroid to the compression force, right, is going to be equal to the total moment arm, A subtracting E, the eccentricity. So actually this E prime, I guess I can rewrite the equation. I'm going to say here E prime is going to be equal to A, which means the moment divided by T, this moment here, the external applied moment, divided by T or C, subtracting E. And for that, I can rewrite my equation when it comes here to the stresses. top and bottom, I can rewrite it this way. Now tension is going to be equal to compression. So I can say, let's say compression divided by AC, right? It's going to be the amount of corrosive forces. And now the same force again, C. I'm going to say times E prime because it's going to be a small moment applied here in the top. Divided by IC, moment of inertia, times this is going to be distance from centroid to the top. So this here, C sub T is going to be the distance from here to there. So you can call this C sub T. And this one here is going to be C bottom. Okay. This is fine. But this is not actually the best form of equation. But this equation here explained to me something is going to be very critical here and very important. This amount of tension force just grown up in the steel, and also the compression force. You add more loading if you have some incremental load in conventional concrete. What's happening? This force here grows as the load increases. So this compression force and tension force is just going to be going up. This is the nature of it. Look here what happened. The amount of pre-stressing that you put here at the beginning is not changing when you're adding more loads, which is kind of weird, right? I understand that I add more load. I need to see here some stresses, right? Some forces in the strands or in the reinforcing bars, and some compression force here is going to be grown up. But in here, the system is completely different. When you add any loads, you are not changing the tension force in the strands. The change is going to be minor. It's going to be almost nothing. You can just ignore it if you like. But what's changing here is going to be the location of the force. Because you are playing here with the compression force location relative to the tension force, with this A. Any questions? Questions? Right? So as you see here, the equation that we are using here, the amount of force, this C, which is the same as T, which is the same as a pre-stressing force, it depends whether it's going to be PI or PE. You say, okay. If you try here PE, it means that you're talking about the effective pre-stressing. If you're talking here about PI, you're talking about the initial pre-stress that you're applying to the beam. All right, let's take you to the next slide set. Has anyone seen the homework yet? Are you guys there? Should we talk about the homework now?
Yes, please.
Okay,
Yes.
all right. Since it's related to that section that we just covered. Concrete beam has a cross-sectional area as shown in this figure. Let's see here 16, 4, 16, and 6 inches. It seemed that they didn't give me here the centroid. I'm just looking here quick, right? I don't have here the centroid, so I need to figure out the location of the centroid. This is why an Excel sheet to find out the centroid and the moment of inertia for this section, and to find out Y top and Y bottom, or you may call it here C top and C bottom, is going to be very good. It's going to help you out because we're going to keep on repeating this. It has an axial load in the centroid of 20 kips. what does it mean by that? I'm gonna have here pre-stressing force, right? It's gonna be 20 kips axial compression. The given moment here is 25 kip foot. They didn't say if this is dead load or live load. They didn't say it's gonna be P or PI. I don't care. It's just gonna be one axial force in the middle of 20 kips, and moment is gonna be 25 kip foot, and it's gonna be positive moment, which means tension is gonna be at the bottom, and compression is gonna be at the top. Let's see what's needed. Number one, determine location of neutral axis, which means the centroid. So, okay, from the bottom of the beam. So give me this dimension here. It's gonna be number one. And of course, once you find this with it, you're gonna be doing the entire section properties or the analysis for it. So, okay. Determine the moment of inertia. Great. Yeah, moment of inertia. I know how to do it for a T section. And the section modulus. How do you do here section modulus? Actually, you're going to have two values, S top and S bottom. What is S top? Say S top equals moment of inertia divided by, if you like to call this C top, I'm going to call it here C top. This one here is going to be C top. And this value here is going to be C bottom. C sub B, which means this distance here. So in this case, it's going to be I divided by C top. In this one, it's going to be I divided by C bottom. So, okay, good. This is easy. Up to number two should be simple. It's easier to determine the combined stress due to axial load and passive moment at the top and the bottom of the section. All right. So I need to bring the same slide set and try to find out the equation. Can someone help me here and tell me what page should I go to? What slide number? Do you think that this is good enough? Yes? No? Is this the right equation? Or should I go here? Should I go to this equations? Or this equation is good? Or should I go to this one with PI and PE? What do you guys think? Should I go to slide number 46? Or it is enough to use slide 42? I'd like to hear from you guys. I'm listening. Which one? 45, excuse me, 42 or 46? Which one do you guys want to use? All right, we'll do 42, just simpler. And I don't have P and PI. Why should I do the other one, right? It's okay. What happened here? They said here that the location of the axial force, the pre-stress is gonna be here. So how much should I use here for E value? I'd like to hear from you guys. How much is E now in my equation?
Should be 0.
Yeah, exactly. So this is gonna be 0. Good. How about the moment here? What moment value should I use? It says here what? 25 kip foot, right? So now I have the moment value, correct? How about the moment of inertia? Where'd you get it from? I'm gonna say, yeah, they asked me here to solve for the moment of inertia. And this one here, which C do you think I need to use? Is it gonna be C top or C bottom? It's gonna be C top, right? Why? Because I'm at the top. Stress on the top. And this one is gonna be C bottom. Good. I said, okay. I guess I'm getting somewhere. So this moment I have the value. I, moment of inertia, I sub G, I have it. Eccentricity is gonna be equal to 0. If eccentricity is gonna be equal to 0, this means this term is gonna be just gone, right? Nothing here. And P force, how much is P? They say 20 kips. Cross-section area. Well, cross-section area, you figured that, right? And with that, figure out the stress problem bubble. Are we good? Questions on this homework, or we're good?
Good, thank you.
All right, great. Now we covered this, you know what to do, and shouldn't take you more than, I would say here, half an hour. I have another homework. I have a given section. Here's a beam section, right? So I'm gonna say, do I have a beam span? I said, yeah, it's right here. Look at this. This can be actually for this beam. Beam span 30 feet. It says here figure 1 and figure 2. Which one do you think is gonna be at the mid span? Which one's gonna be at the support? I'd like to hear from you. Alexander, Flores, can you help me with this? Alex,
Sorry, what was that question?
which section you think? Is this section here at the middle of the span or at the support? This one. What do you expect?
Middle.
So this one is the middle? Or this one's gonna be the middle? You know, look at the chat room. Thank you, Raul. The question was to him, not to you. All right, so actually this section, it has to be at the support. And this section is gonna be in the middle. We discussed this, right? We said that I need the drape here, or I need the eccentricity right here in the middle to counteract the effect of this force. While at the support, I don't want to see any eccentricity. So if my beam is going to look like this, here's the beam, let me just draw it. Gonna draw the strain this way. See, this is gonna be in the middle, it's gonna be coming like this, then coming back like this. It's gonna be the strain. So at the support, it's gonna be this section here. In the middle of the span, I'd like to see here some eccentricity. How much is E that I used to use in my analysis? I'm gonna say E. Can someone help me here with the value of E? Can you give a numerical value?
8.
8 inches. How did you come up with 8 inches? It's gonna be this one here, right? Here's what you said. You said this gonna be 12 inches because I have symmetrical section. 12 subtracting 4 is gonna be 8 inches. And this is gonna be what? I can call this E, eccentricity. All right, now let me go back and read the problem. It says here the cross-section area is gonna be 16 by 24. Yeah, I see that. And F prime C concrete strength is gonna be 5,000 psi. And then it says here figure 1 is at the end of the beam. This is gonna be figure 1, end of the beam, both ends. And figure 2 is gonna be at the middle of the beam, showing the location of the pre-stress force. Yeah, here's a pre-stress force, I understand. Figure 3 shows the beam and the applied load. Here's applied load. Right, let's see what's needed. Moment diagram. Do you guys know how to do moment diagram? You say, yeah, of course. Determine the maximum moment due to loading. Where do you think maximum load is gonna happen? Middle of the span or top of support? As I say, it's gonna be right here. Right? Since you're gonna be there, find out the moment. Can someone help me here with the moment value? How much is it, Gaby? M equals, I need help. $150. How's that? Yes, Mr. Hussein, can you speak? Can you discuss it with me?
Yes, this is PL divided to 4.
Okay, PL 10 times 30 divided by 4. How much is that?
10,
If you have $300 and you'd like to give to 4 people, how much would you give?
Yeah,
How much?
it's 70, 75, yeah.
75. 75
yeah.
what?
Keeps feet,
75 what? Unit?
keeps feet.
Keep foot. Okay.
Yeah.
Not dollar, right?
Yeah.
All right.
Yeah,
All right. So it's gonna be 75. So this is simple. Actually, the problem is so simple. Section moment of inertia. Yeah, this is actually simpler than the previous problem in that sense. Section modulus, you just take I divided by C, and your C here value is going to be equal to 12 inches, right? So, okay. Now determine the bending stress top and bottom of the beam at the midspan and applied load. What equation would you use? I'm going to say use this, but now E, it has a value, right? Because I've been told a minute ago that E is going to be equal to 8 inches, right? I said, okay. So the stress is going to be simple. Determine the section modulus, determine the bending stress, top and bottom, where? At the midspan due to the applied load. Oh, be careful. You can't use the entire equation here, right? Because it says just due to what? Applied load, which means that you just need to find this section of it. It's gonna be M over S. Only that's it. Don't use the entire equation because look at this. You got to be careful, otherwise you may lose points, right? So it says here due to the applied load. Because how much is the pre-stress? Pre-stress is not there. No one told me yet about the amount of pre-stress. So I'm just taking step by step. It says if the pre-stress force equal to 6 kips, determine the stresses top and bottom of the beam due to the pre-stress. Look at this, the pre-stress force. Would that include the loading? No, it is just due to the pre-stress force. It didn't say add the load to it, right? So I just need to do it for the pre-stress force only. At the end of the beam, do you have eccentricity? No, it's gonna be just P over A. So for this one, if you'd like to write it down, it's gonna be P over A. Now, if the pre-stress force is 6 kips, determine the stress top and bottom of the beam due to what? The pre-stress force only at the middle of the beam. Okay, in this case, I'm gonna be using here this equation, right? That I have right there. And actually the question here is gonna be about these two terms together. Maybe just these two. No effect of external moment, right? The applied moment is not considered here. Do not consider this two. Just gonna be these two terms, right? So, okay, this is gonna be good for item number 6. Number 7 here, determine the final combined stresses, which means that you take the stresses from the load plus the stresses here where? Is gonna be from the pre-stressing, which means that you apply this equation. So what is the end? Requirement, the last item here required. The last item here required is gonna be actually about just use this equation here. Right? So actually these two homeworks is really about the use of this equation. And if you really understand it and you can apply this equation safely. Any questions? No, we're good with these two homeworks. So again, the constant A uppercase is going to be equal to 4A divided by L squared. Okay. Don't forget this concept. External moment is going to be equal to internal moment, right? Keep this in mind, please. It's going to be very important for us. The internal moment is going to be coming from the pre-stressing. So your internal moment equals to what? Can someone help me here? When I have some eccentricity of A, internal moment equals, yeah, help, equals to what? Yes? Previous slide set. Go to the end. Moment equals to C times A, correct? or T times A. The force times the eccentricity. Where is the eccentricity here? A. Therefore, the moment is going to be equal to P times, yes, A. This give you the internal moment. About the external moment, how do you guys do the external moment? Can someone help me here? External moment on the beam. How do you guys do it? Hussein? Mr. Hussein? Are you there?
Yeah, I'm here.
I mean, you said it, PL/4, correct?
Yeah,
So this is exactly correct. This is going to be the external moment.
yeah,
External moment is going to be from the beam analysis, right? Internal moment is going to be P times A in this case. So I can simply say external moment is going to be equal to internal moment, right?
right.
Can I say that?
Yes,
Okay, let me write it down. So I'm going to say here, P times A, what is that? Internal moment, right? Correct?
right.
Equals to, what's the external moment if you have uniform load like this? Do you know the equation for it? W times
WL2A.
L squared divided by 8,
Yeah,
right?
right.
And let me put this just to be sure that no one's confused. Correct? Now, if I need to balance, this is going to be external, this internal moment, and it's going to be external moment, right? If I need to balance this W, what P value would I have? Does it make sense for the question? Say P is going to be equal to what? W, right? L squared divided by 8
Right.
times 8, correct?
All right.
That's it. What is W squared divided by 8? It's going to be the moment. You just take the moment divided by 8. You get the amount of pre-stress force that you need. Make sense? I say, okay, yeah, makes sense. Let's see here. With this load balancing, is this true? Can I use this simple analogy? Because I made it very simple, right? I just say external moment equals to internal moment. Just set them equal to each other. I was able to solve for P. This is going to be balancing this weight. This weight is coming from the top. And I'd like to balance it. Put another weight or another loading is going to be pushing this up to balance it, to make at the end this beam to be flat. So it's okay. Let's do it the hard way, because that was actually simple. That really makes sense. Just external moment equals to internal moment. Look at this method here. I have here some load P, right? And this is going to be integration of this load, because this is trying to balance this. This is going to be the second derivative of this Y. Once you multiply by P, you'll get here the W, the load intensity. So, okay. Take this load here equal to P second derivative. What is the second derivative of this Y? Because I have the equation, I'm going to say, let me go back here. Look at the equation. Y equals for A x squared divided by L squared. Second derivative is going to be what? It's going to be just 4A over L squared, because this is going to be X, and then it's going to be nothing. It's going to be 1, right? So second derivative of Y is going to be 4A divided by L squared, which means it's A uppercase. Can I take it here? 4A divided by L squared, and then you have here 2A, right? Therefore, W equals 8PA divided by L squared. Okay. And look at this equation here. If you set this W equals to that, P is going to be equal to W L squared divided by 8A. This is the same equation, because this equation here, it's true, it doesn't say this way, but this is what I'm going to put it right there. I'm going to say this is going to be internal moment. and this one is external moment. Right? If you like to treat it this way, you're good. If you like to make it complex and do differentiations, it'll be also good. But for me, I just set them equal to each other, right? It's just easier. So this force here, P, that you see here in this equation, is giving the amount of pre-stress force that you need to balance W with. So for example, if I tell you here that your dead load equals 1 kg per foot, and you like to balance 75% of it, so what would you do? And you have the span, you have the drape, you have the whole thing. So it's gonna be very simple, because all what you need to say, if I may write this numerical problem, quick problem, you say find out the amount of force. Let's say span. Let me write the whole thing. Span equals to what? Can someone give me some numbers to work with? Can someone suggest here some values?
24.
24 or 44?
24.
24. Okay, feet, good. One very important thing, when you do the stress analysis and the homework, be careful about units, because the moment here is going to be in foot and the moment of inertia is going to be in inches. So be careful about units. All right. So the span is 24. How about the weight? Dead load is how much? Give me some value. Are you good with 1 kg per foot? Yes.
Yes.
Okay, good. How about A, the drape? How many inches are we talking about? 100 inches? 12 inches? 24 inches?
1 inch.
24? 12? Yes. How much?
6.
No, 6 is going to be very small for 24 feet. We're going to say here 16 inch, okay? All right. Question is, someone here is telling me balance 75% of dead load. I'm going to say 75% of the dead load. So, okay, good. Which means this W is going to be equal to 75% of this 1 kg. So W equals 0.75 times 1 equals 0.75 kg per foot, right? Are we good? This is what we're trying here to balance, just 0.75 kg per foot. Why? Because total dead load is 1, and I want to balance only 75% of it. So, okay. The question is, how much axial load you need for pre-stressing force? Say P equals the load, 0.75, times L squared, we're going to say 24 squared, right? Divided by 8 times A. How much is A that I need to use here? Yes,
16 divided by 12.
yeah, thank you very much. Yeah, 16 divided by 12. And this is exactly what I was talking about. You got to be careful about units, because you'd like here to put everything in feet. Why? Because this 24, that was in feet, and this 16 is in inches. So maybe you'd like to put everything in feet. Say, how much is that? How much force do I need? Anyone with calculator?
40.5.
That's it, 40.5. Let me write it down. So 40.5 what? Kips or pounds? Say kips. So for this given beam, with this given information, if you put pre-stressing force of 40.5, it's going to be balancing 75% of the dead load. Not a bad concept, right? At least now I understand that when you're doing here pre-stress, actually you're trying to balance some loads coming from the top, and you just control the amount of pre-stressing that you put in there. And this makes sense to me. What is this about? All All right. So this is gonna happen only if I have uniform load. I'm gonna have here parabolic profile, correct? But if I have hard section, like in here, I guess I'm gonna have different story, correct? Because the moment is not W squared divided by 8, the moment is gonna be here PL divided by 4. It's gonna be different equation. But my understanding is I need to look here at the maximum moment, which means W squared divided by 8, and just do it this way, because this is just simpler. I'm gonna say external moment, internal moment. External, you calculate out yourself. It depends on the beam, the condition of the beam. The internal is gonna be the same. It's gonna be just P times A. Eccentricity times the axial force, the pre-stressed force. Okay.
Another question.
Yeah. Very
So
good.
we just care about the maximum internal moment, basically.
For the load balancing, yes.
Yes. So we don't care
Because-
about the shape of itself, correct?
The shape of the drape, you'd like it depends on the load. Let's say that I know for sure. I'm gonna take you back here. Very good question. Thank you for asking this. I know for sure that the equipment I'm supporting here is gonna be just one heavy equipment. Is gonna be right here, right? No uniform load. Versus I'm gonna have here, let's say, a beam or a slab in the residential area, or let's say residential building, or maybe office building. So I know most likely load is gonna be uniform, right? Versus maybe something supporting equipment at the roof, some roof, right? And I know it's gonna be just concentrated load, no uniform load. So I guess I know which drape is good for what, right?
Right.
So if you have like uniform load, you don't know exactly what to expect in terms of the load distribution, you're gonna be doing this. If you know that this equipment is gonna be right in the middle, no change in location, you'd go with this.
Got it. That makes sense.
Yeah.
Thank you.
No problem. Okay. So at the bottom, I'm gonna put here the cable. You see here how it goes, then go to the top. Goes also to the top, this drape, because I'm expecting here uniform load. So, okay. And this comes here to the centroid, the middle span. I'm gonna have this E, the maximum. Look what happened here to the axial force. When I was doing the axial force in my analysis, I usually assume the axial force to be like this. Correct? To be straight. But reality is gonna have an angle, because you cannot bring this cable and just make it straight here. You cannot do it this way. It's gonna have this angle theta. Therefore, you're gonna have, when it come here to the horizontal force, it's gonna be not
Closer.
really P, it's gonna be a little bit different, right? And also, you're gonna have a vertical component. Correct? Because you're gonna have here two forces. If you do the analysis of this force, if you resolve it, you're gonna have here two components. First, if I'd like here to consider this to be 0 and 0, what's gonna be the equation for this? Let's say equation. Yeah, equation is gonna be a little bit different. It's gonna be the same concept. The equation here is just A times X. The equation here is gonna be X over L by ratio and things like this. It's okay. You know the theta here, this angle. This angle is gonna be the slope of, if you like, this is gonna be the slope of the cable, right? If you like to figure out this slope, if you know the amount of E and you're interested in the theta, you just need to find out the first derivative is gonna be the slope, dy by dx. Yeah, you can do it this way. If you look for the curvature, you can do the second derivative. Okay, yeah, I hear about curvature. What's curvature? Curvature, this phi is gonna be equal to 1 over rho, which means the radius of curvature. What I really care about is gonna be how much force is gonna be pushing up and down, and what's gonna happen, which force that I need to consider to be effective. So I'm gonna come here at the end. I'm gonna say, you know what? Here is the component. The vertical component is gonna be equal to 4 PE over L. So how did you come up with this? So, okay, this is simple. How much moment do you expect when you have a case like this? Do you expect here any moment coming from this drape? And look at this equation here. PE, what is P times E? What do you call this? Internal moment, right? So P times E is going to be internal moment. So, okay, yeah, P times E is going to be internal moment. I have here some moment. When you divide by the total span, meaning what? You're trying to find out here some forces going to be going up, right? Or going this way. When you take this moment here, divide by the entire span, you're going to get here two forces, right? And one of them, so you take here PE divided by L. It's okay, I'm going to have a force going this way and force coming this way. Does it make sense or no? Let's give you one moment here in the middle. So actually, in reality, when you have any moment, just ignore any given loading, right? When you have any moment here, what is this doing? It is pushing this beam up. As if you're going to have two sections here of the beam. One's going to be like this, and the other one's going to be like this, right? Does it make sense? You're trying to push them up. You push them up from here. Meaning that you're going to be applied moment coming this way. If I may draw it, try here to draw it with this. You can have another moment coming this way, right? You guys agree? You have two moments coming this way. They're trying to push this up. If you take each one of this moment, and this moment here is going to be equal to 0, right? Because also someone's going to say, you know what, if I may have another moment coming here, the amount of vertical force is going to be equal to the summation of these two moments divided by the span. So I'm going to say this actually is going to be M, is going to be L over 2. This is going to be ML over 2. So I'm going to have a force here trying to push this up or down. This is going to be now the question to you guys. What is this pre-stressing doing? Is this pushing the beam up from this here from support? Is going to be pushing it down? Is a question to you. How do you feel about the mechanism of this or the performance of this?
Down.
It's going to be pushing down. This means the pre-stress beam itself, after they put the pre-stressing, is going to be pushing down the support. Now, when you have here in reaction, like in a shear, is this helping the reaction or opposite to the reaction? Or when it comes to shear, what is this doing to the shear? Reducing the shear or increasing the shear on the beam? Yes? All right, so what is the shear? The shear is going to be a force. It's trying to take this block of the beam and bring it down. Let's say here's a beam, right? Let's say here's a beam, right? And this going to be the shear location. She's trying to bring this down, correct? It's going to be something like this. As if I'm pushing this down and pushing this up, correct? Is this pre-stress helping the beam against the shear or damaging the beam more with the shear? In other words, against or with the shear?
Against.
It's against.
Yeah.
Against the shear, right? So actually it is helping the beam. This is why pre-stressed beams are stronger when it comes to shear. Why? Because the pre-stressing effect itself, it's against the reaction, against the shear that you impose on the beam. Does this make sense? Yeah, absolutely makes sense. Look at this beam here. From the load balancing thing. This gave me the applied force, right? Let me go back here. Here's the applied force. What does he do? They create shear to bring this piece up and this piece down. So here's the beam. One piece is going to be here, Here's the other section of it, right? Let's say, and what this loading is doing is trying to push this down like this, correct? What is this trying to do? This loading, it's against that. So actually it's doing this to the beam. It's causing shear, but in the other direction. It's gonna be opposite to the applied shear. So actually it is opposite to the applied shear, which means it is helping the beam to resist the applied shear from the loading. So it's good action. It makes the shear stronger. So the shear equation that you used to see in the conventional concrete now is going to be different, and it's going to give you high results for pre-stressed beams. So just to make it simple, if you like to use the second derivative equation, it's fine. If you like to use external moment equals to internal moment, it's going to be also fine, knowing that you're going to have maybe some reactions coming here at the end from the way that you push this beam up. All right, now in the load balancing, we have some pre-solved problems for you, and you have a table for it. If you just put this to be straight, right? If you'd like here to put the cable to be straight, your moment here is going to be equal to P times E, pre-stressing times E. It's going to be just straight. And this means in this case, the equivalent loading to this, as if you put a couple of moments, one moment at each end. You're trying here to put pressure, right? And it's going to be like moment coming this way from both ends. If you like to figure out the camber, you can figure it out with this equation here. So this give you some equation to go and find out approximate value for the camber. But we need, this is going to be really important for us to understand what is this doing to us. So the way that you're doing here, this pre-stressing, if it's going to be straight, it's going to be actually, this is going to be what you're doing here to the beam, as if you put two moments at each end and just try to push it up. If you hard the cable this way, right, the equivalent load that you put there is going to be equal to 4P over L. What is that? We will say 4P over L. Let me try to understand this. This means that P, right, the force that you put there, if you like to balance, is going to be equal to, look at this P force, right, or the load that you put there against it, is going to be equal to the moment divided by E. And this is as if you're putting here a force opposite to the action, right, of the expected load is going to be just pushing it up. And this W force, again, is going to be equal to the moment, right, divided by E. Let's look here if you have drape, like parabolic shape. So again, this load is going to be equal to what? Again, the moment, right? Because W squared divided by 8 is going to be equal to P times E, which means a moment. And if you put it this way, as if you push here with two forces, one is going to be at each corner. So you put this one as if you just choose one force up. Put two as if you push here with two forces. You put uniform or parabolic as if you have uniform load. This is what you need to understand, what to expect. Now, this discussion here is also about the location of the force, and when it goes up and it goes down. You start to apply here some force. At the beginning, this eccentricity is going to be equal to 0, right, between the two forces, and you start to apply some loads. It's going to be going up. And at the beginning, if you have no loads, at the beginning, right, if you have no loads, it means that you're not balancing any loads. Why? Because both of these two forces are going to be aligned. They're going to be in the same location. But once you start here to apply some load, it's going to be 100% balanced. To a point that you reach this balanced load WB when the compression force is going to be right at the neutral axis. And with that, these two forces, they're going to be aligned with each other. At that point, you call this the balanced load. And once you're at the balanced load, the other question is going to be how much stress would you have on the beam? And what equation would you use? Because now the external moment is going to be the same as the internal moment. which in this case is gonna be the balanced load. Give me a second here. I guess I'm gonna stop here for today. Since it's gonna be a Zoom day, I'll let you go. And I'll see you next Thursday. And if you guys look at the homework, you see here that homework, when is the homework is gonna do? Can someone here please remind me if you can open it? I just want to be sure this is done the way that we agreed on.